Okay, let's get started. Good morning. The topic of today's lecture is energy carriers and size effects, and today we're going to start to learn about how the properties of nanostructures depend on their size and develop a few formalisms that we'll build upon in the next three lectures where we'll talk about specific categories of properties: electrical, thermal, and mechanical properties. Well, before we start, a few announcements. First, by a show of hands, can you tell me if you're here but you are auditing the course and not taking it for credit? Raise your hands high. Okay, so that's like 4 or 5 of you. I'm just trying to get a sense of how many people will have the course for credit so we can divide into project teams and for some other assignments. Second, because of the level of enrollment, I'm happy to say we have a GSI, and the GSI is Mustafa Bedawi. He isn't here today, but he will have office hours every week. We'll announce the location by email. His office hours will be 4:30 to 6:30 on Thursdays. And then we will likely have an additional office hour close to the date of each problem set. For example, on Sunday or on Tuesday, just before the problem set is due in each case. And he'll be helping with things in general and grading the assignments and another resource for you all in terms of working on the homeworks and on the other project-related assignments. As you may have seen already, I just posted the first problem set. This contains some material which we've discussed already, some from today and some from the next few lectures. It formally goes through the lecture on Monday, February 1. You only need a little bit from Monday, February 1. So, of course, it always helps if you start early, and there are some things you can do right now. As you know, we have 4 problem sets. I think each one is pretty comprehensive and would take quite a bit of time. I encourage you, as it says on the problem set, to get together and talk about the problems together. However, I need each of your solutions to be prepared independently, which means you can't sit down and say, all right, you know, let's compare our answers. You can talk about how you're going to solve the problem, but I want you all to formulate it separately. And it's sometimes pretty clear if the problems look very much the same, I mean, your solutions look very much the same. Also, to be fully honest, a lot of the problem sets are very much the same as they were in past years because I like the problems that I've set up. And that also means that I don't want you to consult solutions from prior versions of the course, talk to students who've seen the course in the past, look at their graded homeworks, or so on. That's not allowed, so I want you to come up with your solutions individually. And you can see me or Mustafa with questions. As I mentioned before, about having an extra session, kind of a mini lecture on literature searching, what I've decided to do instead is I had the video folks pull up the video of that session from last year. And so if you go on the video list for where you see the lectures from now, you'll see one called the lab session, and that's where you can watch about it. And I'll post the related materials for that as well. That's just talking about using databases and RSS feeds for searching for journal articles if that's something that you're not familiar with and want to learn a bit more about. And then last, there have been a couple changes to the syllabus, which has been uploaded again just this morning. And the first change is that instead of this literature review assignment, which I mentioned but didn't define, because of the increased enrollment in the class, we've decided we're going to have a video assignment, and we'll post this next week. And roughly before we detail it, what this means is it'll be a team assignment where we're going to ask you to pick from a list of concepts or subjects from the various lectures and covering the topics up until the first exam, and create a 5-minute video describing that concept. So you can have slides, you can build things, you can do whatever you want, and hopefully it's something that we can put up on the web for others to see. And then I also initially had a percentage of the grade for attendance and participation, either 5 or 10%, also because we have more people in the course as before, and also we're not doing these in-class literature reviews. We're going to convert that to an equivalent percentage of the grade based on peer review of other teams' videos and project reports. And details of that will be announced later. So you don't need to worry about that now, but just to let you know, those are the 2 minor changes that we're making to the syllabus and the structure of assignments. Okay. Are there any other questions before we start? Okay, so last time we talked about characterization of nanostructures, and we didn't get through the whole thing, but we mainly focused on microscopy, optical microscopy, electron microscopy, and scanning probe microscopy. And the theme here is that we want to have a working knowledge of what these techniques are called and how they operate and what their capabilities and limitations are. And the fourth problem on the first problem set will kind of get at this issue with relation to between techniques and specific nanostructures or specific groups of nanostructures. And we can use microscopy to characterize materials. We can use surface analysis using electrons and X-rays to get information about the surface and chemical structure. And then we can also use optical spectroscopy. And the last two categories we didn't really touch on, and I'll just give a little bit of a flavor of that, and then I'll leave the rest of the slides for you to look at on your own for the problem set, and also I'll try to pull in examples of the specific other techniques as we go through the upcoming lectures. And one of the important things to realize is that when we want to look at nanostructures, we want to get different types of information. We want to get information on size and structure, and also image on the configuration and nature of the atoms, chemical information and structural information. And based on the technique we choose, we can get a combination of these pieces of information, and also there are often trade-offs. So for example, a lot of the microscopy techniques we talked about for nanostructures are really pushing the resolution limit down toward the atomic scale. And there are other techniques that maybe don't have such high resolution, but can give us chemical information on the nature of the atoms, the configuration of the bonding, and so on. And when we closed last time, we were talking about the use of X-rays, X-ray diffraction, and X-ray scattering to interact with the atoms in a crystal and therefore create an image or create a spectrum that lets us calculate, in the case of an ideal crystal, what the spacing between the atoms are. And that can also be done with some light techniques, but the basic idea is that because the wavelength of the X-rays is smaller than the spacing between the atoms, we can take advantage of that interaction to get information about the structure of the material. And you can do X-ray diffraction and electron diffraction, and you can do it using a very high energy X-ray beam, such as a synchrotron source, or you can do it using a relatively more tractable in-lab apparatus, a desktop source, or you can do it in an electron microscope. And we saw the pictures of doing electron diffraction in the TEM. So kind of as a recap, can anyone tell me, for example, how was this picture on the top taken? Just raise your hand or shout out the answer.
TM.
TM. And so why was it taken by the TM? How can you tell?
Because the particles are so tiny.
So the particles are tiny, so basically, yeah, one thing you can always do is look at the length scale, but this looks like we see the contrast of the individual atoms in this particle, and this is a classic TM image. And this is a TM image as well. Who can say why does this area of the structure look darker than this area? Someone else before you answer. Anyone else?
The sheet.
Sorry?
The sheet.
It is the seed, but why would it be darker, do you think, in terms of how it would interact with the beam? Right back there.
It's a different material, and so it scatters the electrons differently.
It's a different material that scatters electrons differently, and it has a higher electron density. So this element may be gold, and this may be silicon, and this is heavier than that one, and therefore it's, quote, darker or harder to see through it. So that's a good answer. And then how about this image in the middle here, this bunch of carbon nanotubes?
SEM.
SEM image, exactly. And so now we see we're not looking at an individual structure, but we're looking at a collection of structures. And you couldn't really get a TM beam to penetrate through this forest. In this case, the electrons are scattering off the material, and that's how we're generating the image. And how about this image down on the bottom right? So this is a picture of some graphene sheets sitting on a substrate. And the resolution is pretty high, and let me say that the color here corresponds to the height. So maybe this is like 2 layers of graphene, and that's 1 layer.
AFM?
AFM. So that's an AFM image where we're looking at the topography of the substrate. And maybe we could take a picture like this in SEM, but we couldn't get such fine contrast and quantitative measurement of the height. So an example of some of the techniques that remain from the lecture last time are these techniques where we use surface analysis. We basically hit a surface with a beam to get some chemical information and some structural information about the material. So I just want to mention one here as a flavor of what you might look in onto your own, and that's called X-ray photoelectron spectroscopy. And in general, a lot of these techniques depend on what you hit the sample with and what you measure. So in this case, you hit the sample with a focused beam of X-rays, and you look at the emitted electrons. And this can be done is typically done in a vacuum chamber with an X-ray beam and with a detector. And at the most basic level, by looking at the emission spectrum of the electrons and relating that to what you know to be the electron energy of different materials, then you can measure what the material is. So the spectrometer uses this mechanism and follows this simple equation where you know the energy of the X-rays you put in. You measure the kinetic energies, the kinetic energy of the emitted electrons that get ejected from your material, and you have a calibrated parameter, which is the work function of the spectrometer, and then you get a resulting binding energy, and this binding energy corresponds to the material of interest. And you do this in a spectrum fashion, and you basically count the number of emitted electrons you get with a certain resulting binding energy. And if you put a piece of material in your spectrometer, you get a spectrum. And if you know, for example, what the binding energy of an oxygen peak or a carbon peak or a silicon peak would be, you can then get some qualitative and quantitative information on the characteristics of the material. And the important thing here is also that the binding energy for a particular element depends on its bonding configuration. So if you have, say, silicon bonded to one oxygen or silicon bonded to two oxygens, you're going to have peaks in different places. And the precise details aren't important for us, but all this information is very well tabulated and calibrated. So, for example, a lot of materials have different oxidation states, for example, like iron, and you can look at the peaks that have been measured with high precision, and you can use that as a means of getting detailed information of what you're looking at. So, for example, one application of XPS is to, for example, look at nanoparticles on a substrate and determine what the composition of the catalyst is. And then, when we talk about growth of carbon nanotubes in several weeks, we'll learn that iron is a typical catalyst. You typically take iron nanoparticles and put them on a substrate, and there's some debate whether the particles that actually grow the nanotubes are iron, metallic iron, Fe, or there's some iron oxide. Because when you expose the small particles of iron to an atmosphere that even contains a little bit of oxygen, that basically is an inert gas, which always contains a little bit of oxygen impurity, it's very easy to oxidize the particles. So by using this XPS technique, sometimes actually during the growth using specialized instruments, people can, for example, try to get information on how the catalyst evolves. So these are just these are just sort of sample spectra from XPS. So here you see they've taken a piece of a spectrum giving a small window of binding energies, and this axis is not labeled, but this is the intensity. And here what they're trying to analyze here is how the catalyst evolves, how the peaks evolve as the catalyst is annealed and growth occurs. So let's just look at this one for now. If you see here, they've labeled the position of an iron oxide peak with this blue line here, and as the catalyst is annealed, they show that it evolves more into a metallic iron state. And so this is enough for now, and you can see they have precise relationships also for the position of the peaks that correspond to the carbon nanotubes or graphite peaks. And actually there are slightly different peak positions if you have planar graphite or tubular graphite. But we'll probably see this example more later when we talk about nanotubes. I just wanted to give you an example of what one of these spectra looks like and how this is another way that is another technique that's used to do surface and chemical analysis of materials. And there are a number of facilities if you're doing or interested in getting into work in characterization of materials on U of M's campus. These are all on North Campus, and for example, the EMAL or Electron Microbeam Analysis Lab has a whole bunch of electron microscopes, has an XPS machine, has a focused ion beam, which can be used to mill small samples. There is an X-ray lab, which is in the Gerstacker building just down the street, and there's also an ion beam lab. And these are just on North Campus. There are a whole bunch of different shared facilities. And you can look into these if you actually want to use or see some of this kind of this kind of equipment. Okay, are there any questions about the characterization subject? Okay, so today we're going to start to talk about how we're going to think about the properties of materials. We saw how the sizes of nanostructures can be pretty special. There can be this kind of discretization in size at the magic number level. And we also saw how in the case of carbon nanotubes, the way we wrap the graphene into a tube depends precisely on how the atoms are organized. And there are also these kinds of like special conditions for matching of the atoms. So now we're going to understand why those changes in size equal to changes in properties. And so today's agenda will take us first through a general description of energy carriers, thinking more at the small scale level how energy, electrons, light, and heat are transported in materials and between materials. And then we'll start to think about how these energy carriers interact with one another and how they interact with the material, and end up with an example where we consider how the size of semiconductor particles, those color-changing, those bottles with different colors, depends on their size. And that'll be based on what's called a simple model, often called the particle in a box, where you imagine you have energy carriers represented as waves, and the allowable energy states of those carriers are restricted because the box is so small. And it's kind of a dreamy concept and a very simplistic concept, but it turns out that just that simple way of modeling it lets us get a pretty good prediction of, for example, why different sizes of these semiconductor particles have different colors. And the readings on C-Tools today, I think a good intro is the first one by Rogers and colleagues, which is from an introductory book on nanotechnology and small systems. There is a paper by Alvasados on semiconductor crystals and quantum dots. And then there is a longer paper which talks more so specifically about optical and electronic properties of nanostructures. So I'd say this is the most important reading at the top here. You can read these a bit more lightly as references. And then in the extras folder, I have chapters from books. And we don't need to be responsible for all the material in these chapters, but they're good references if you want to learn more about the details of energy transport at the nanoscale. And the problem in problem set 1 that asks about the optical properties of nanoparticles, there are a couple of tables in Gapanenko which will be useful for looking up some of the constants, as is mentioned on the problem set itself. So what I want to do is try to generate a picture of how energy is transported at a small scale. And we want to think of carriers of energy as being things that carry, for example, electrons or carry heat, or how light is transported. And we can generally divide this into 2 categories. We can think of electrical transport, and we can think of thermal transport. And the general picture I want to create is that we can think of the carriers of energy as sort of little elements, or if you will, little particles. And if you've read about this in the past or heard about it in the past, you often hear that people talk about the electrons in a metal as being a gas. And this idea of electron gas is that if you transport electrons from one side of a material to another, for example, you have a metal on one side and a metal on the other side, and you're applying a voltage, you can pull electrons off the metal and move them to the other side, and they behave in a qualitative way like atoms or molecules of a gas, which means that they have some velocity and they can interact with each other, and they can also interact with the edge of the material or the walls of the container. And likewise, we can think of transport of heat from the hot side of material to the cold side of material as being by conduction, for example, where heat is flowing through the material, and in that case you actually have heat flowing because of vibration of the lattice, or for example by convection, where it's the same mechanism but you actually have physical transport of the atoms or molecules through the space. But the general picture here is that we're just going to think about our material as a sort of box, and we're going to think about what may be different as the particles we have inside this box have different characteristics. And as we consider changing the size of that box, getting it smaller and smaller, so the interactions between the particles and the interactions between the particles and the sides of the box become important. And we'll learn that all the carriers that we're going to define in a second have what we'll call wave-like and particle-like aspects. And a wave is something that has sort of a distributed property. And we know about sine waves and cosine waves and how they have wavelength and energy and momentum, as well as particles being thought as more so as having a discretized energy and a discretized property. It's like all here in this little space, or it's not here. And a very fundamental concept that leads to understanding the transport properties of materials is that things can be both wave-like and particle-like. And we'll see an example of this and a way to think about this in a few slides as well. So first I want to define what we're going to call a basic 4 energy carriers for materials. And the first one is an electron. So we know that electrons in atoms and in materials are subatomic particles carrying a negative charge. And the interaction between electrons is the main cause of chemical bonding. We have ionic bonds or covalent bonds, and with 2 atoms, such as in silicon oxide, get together, there's some interaction between the electrons at the outer extents of the atom, and you form a bond. So something like gold, as shown here, has a whole bunch of electrons around it. And remember from chemistry that these are in different orbitals or different energy levels, and the energy depends on the position with respect to the center of the atom. The second fundamental energy carrier that I want us to think about is a photon. And a photon is a quantum or a sort of a basic unit of the electromagnetic field, or a basic unit of light. So in the sun, there's a chemical reaction that produces electromagnetic radiation, and the sun issues photons down upon to the Earth. And the elementary way that we quantify the energy of a photon is h, or Planck's constant, as we'll see later, multiplied by nu, or the frequency of the electromagnetic radiation. And that h times nu applies to all electromagnetic waves, and light just happens to be in the electromagnetic wave that we can see, and that's why we call it visible light. And then we're going to talk about phonons, which sounds like photon, except a phonon is considered to be a mode of a vibration of a lattice. And you can think of every material as having mechanical vibrations, except when we talk about phonons, we're particularly going to be talking about vibrations of materials at the atomic level. So a beam that you might hit with a hammer will have a certain resonant frequency and therefore a mode of vibration. And likewise, the atoms inside a crystal will have many modes of vibration, except those frequencies of vibration will probably be a lot higher than the beam that will be vibrating at the macro scale. And we'll see this a lot in the case of thermal properties, because phonon transport is the primary means of heat conduction in insulating solids. And this idea of thinking about bonds or connections between atoms as a simple spring is also one that'll be fundamental to the way we think about mechanical properties. Because when you get down to a scale of a structure of individual atoms, imagine pulling on a nanotube, we can think with some reasonable degree of certainty of that as a collection of springs, and we can use those simple spring models to extract actually a good idea of things like the stiffness and the strength of the material. And the last energy carrier that we'll talk about is sort of just a formalism. It's not really a carrier on its own, and that's what's called an exciton. And the reason it's called a quasi-particle because it's not really a particle, but it's talked of as a state consisting of both an electron and a hole. And you hear the term exciton generation in the context of when light hits a material, such as light hitting a quantum dot, as we'll talk about later, and exciting an electron to an excited state or a higher energy level. And that leaves what we call a hole behind, and the exciton is sort of the electron and the hole together. So the exciton in that regard is a formalism for transporting energy without transporting net charge, because the electron and the hole add up to a net charge of 0. And this picture at the bottom is just showing a schematic of light hitting a material and generating and exciting an electron, leaving the hole or sort of the vacancy behind, and then they recombine after the electron and the hole go in opposite directions. And that's also formalism, for example, for considering how a solar cell works. When you cause that charge separation and then you generate a potential because of it, if you design the configuration to accept that. So one of the sort of fundamental experiments that got scientists starting to think about how energy carriers interact in materials and how, as we'll see later, the properties of materials starts to depend on their size, was this observation of what's called the photoelectric effect. And in this experiment, which was done long ago, what was found is that if you take a setup such as this, typically done in vacuum, where you have a pair of pieces of metal, which here are called metal electrodes, and you hit one of the sides, one of the pieces of metal with light, and you can measure the current flowing through this wire, which is connected to both metal plates, you actually measure a current. And it's like, well, what's going on? How is light hitting this material generating a current? So what's actually happening is if the energy of your incident light, the energy of that photon, exceeds the energy difference between what's called the Fermi level of the metal and the energy level of the vacuum, and we'll define these terms in detail more so next time when we talk about electrical properties, then you can excite an electron from the metal, and then that can hit the other side, and you can collect it as a current, and you measure a flow of electrons around this circuit. And this was explained by Einstein many decades ago, and one of the really interesting observations back then was that if you could measure the kinetic energy of the electrons that you excited, you might first guess that, well, that's going to be higher if the intensity of the light is higher. If I'm turning on a brighter light bulb, then I might get a higher electron energy, and actually no, it's not the case. The electron kinetic energy is independent of the intensity of radiation that you put. However, the rate of electron emission, or essentially the current that you measure through this circuit, is going to depend on the intensity, because if you're hitting your material with more photons, then you're going to be generating more electrons across the circuit. And the reason why this is constant is because this effective gap, or this difference between energies, is determining the energy of the electron that is excited and passes through this circuit. And now we'll talk about another set of experiments that lets us build this kind of picture. And an experiment also done back in the day was one that lets us think about how these energy carriers can behave like particles and like waves, meaning they can behave like they have all their energy and all their characteristics in this one spot, like a local delta function, or they can behave collectively like they have a distribution of characteristics. So let's consider this experiment, which is called the double slit experiment. And first, imagine that we have a gun out here, and now we can think of having like a big gun, a macroscopic gun, or something that's shooting ping pong balls or BBs. And we have a plate here that has 2 holes in it, or a wall with 2 holes in it. And so this wall, we can consider, will perfectly absorb all the bullets that hit the wall, and the bullets that pass through are not disturbed in any way. And you see that if you have a backstop here that also perfectly absorbs the balls, and you count the number of balls that hits any particular point, you see that you have, although the balls hit each place individually, and you can assume that they don't interact with one another, you end up with, if you shoot enough bullets through these 2 holes, a distribution of you could say, intensity or number of bullets or BBs that have hit this plate. And you could say, for example, if you blocked the second hole, then you would have a distribution like so that only corresponds to the way the bullets transmit through the first hole. The opposite of, if you block the first hole, and then if you leave them both open, you get this summed distribution. And this kind of lets us think about, well, gee, these are particles, but this kind of looks like a wave, and this looks like the superposition of a couple of probability distributions that give kind of wave-like character. And that's exactly what we want to think about. And actually, the same case would happen if we did an experiment with a wave. So now imagine, instead of having bullets coming out of a gun, we have a source of something continuous. We, for example, have a plate sitting in a pool of water, and we have a source that creates this ideal circular wave. So it's, say, touching the water, so you have this circular wavefront moving, and now we have the same kind of wall that now lets the waves transmit through or blocks them in these areas, and we have a backstop where we can measure the intensity of the wave energy that gets transmitted and absorbed here. And for example, you can see that if you have just one of the slits, you get a distribution like this. And if you have another slit, you get a distribution like this. But the distribution looks much different if you have both slits open because of the characteristics of constructive and destructive interference of the waves. So here's a case where we're using a wave source to generate a distribution like this. And this interference can be, represented mathematically based on the sum of these two waves here. And what led people start to think about how how these fundamental energy carriers can behave both like particles and like waves was when this experiment was done with electrons. So now you have an electron gun. So this is probably operating in vacuum, and you can think of this as kind of like a filament that emits at the top of an electron microscope. And you have, say, a piece of metal here with two holes, and you know that, well, you think that an electron is kind of like a particle. It's a quantized amount of energy that is the fundamental subatomic particle in an atom, and you can certainly strip off an electron like was ejected in the photoelectric experiment. But if you use this electron gun to do this experiment through these two slits, if you have just one slit open, you get this nice smooth monotonic distribution. The same thing with the second slit. But if you leave both slits open, you get an interference pattern that indicates that these, quote, particles, these subatomic particles, can interfere just like the waves in water did. And this lets us sort of set up this idea of energy carriers behaving both like particles and like waves. And where I want us to end up is the thought that depending on the size scale of our system, we can consider the carriers to behave more like particles or more like waves. We can represent them by a more, you could say, continuous distribution or a discrete distribution. And that'll let us think about how the size of the system determines the allowable energy levels. And these are just some pictures from someone who's done the electron slit experiment, actually done at Hitachi. And this is a snapshot of the detector screen, so like a CCD, kind of like a digital camera that can basically detect the impact of electrons on a particular position. And what you see here is as the number of electrons increases, this is basically recording the time history. It's like throwing darts against the wall of all the electrons that hit. You can imagine that if you only throw a few electrons at it, you can see that they look like pretty much discrete positions. And if you have more and more electrons incident upon it, basically taking a longer snapshot, you start to see the effect of interference and the appearance of these waves. And basically this is telling us that the energy of these electrons, although it's highest in what we'd call the position of the particle, is actually a distribution in space and time. And the energy from one electron can interfere with the energy distribution from another electron that is at a particular distance. And it's this interference of the wave-like characteristics of the electrons that eventually lets this picture be produced when we've taken enough samples. And this can be very loosely analogous to a case where you have like a low density of carriers in a material and a larger density.
That also happens if you only sample one at a time, and also with light. The experiments have both been done. You still form this interference pattern, even though they don't interfere with each other.
Okay. Okay. So now let's talk a bit about this picture of carriers as particles. And I want to define a term that we'll call the mean free path. And the definition of the mean free path is the time between collisions of the individual carriers we're going to consider. And so we can call a term that's often used is the term called scattering. And scattering means when one carrier hits another, or one electron hits another, or an electron hits a boundary of a material. And we need to have a lot of collisions between these carriers to produce the macroscopic laws that govern the properties of materials that we think about when we think about a wire, for example, having a resistance that's proportional to its length or inversely proportional to its cross-sectional area. And the same things apply for example, Fourier's law for heat conduction or Newtonian laws for shear stresses. However, when the mean free path of the carriers is comparable to the size of the system or the size of the box that we're considering, there aren't so many collisions, you could say, per unit time, and the effects of the boundaries become more important. And this is what people call as sort of a classical size effect. Basically, when we take the size of our system down to be so small that the interactions between the carriers and the boundaries are more important relative to the interactions between the carriers and one another. And an example of, for example, a classical size effect that's observed is, for example, how the thermal conductivity of thin films depends on the thickness of the film. And so if you have, for example, a film of silicon, a thin film of silicon, and here we're plotting the thickness of the film, and this is in meters, so 10 to the minus 7 meters is about 100 nanometers, and 10 to the minus 8 meters is 10 nanometers. And what is seen is that because of scattering or of the heat transfer or the phonon vibrations, the lattice vibrations that carry heat through the material, as we'll see in a couple lectures, is more prominent or has a greater effect on the transport as the thickness goes down, then you see an effective reduction in the thermal conductivity. And the details here aren't important, but the case for a thin film, which is flat, is different than the case of, say, a square wire or a circular wire. And in principle here, the thermal conductivity of the square wire is lower because you have more boundary per unit volume, because instead of having just one side or one boundary on the top and one boundary on the bottom, you have two extra boundaries on the side like so. So here's a case where just qualitatively these interactions between the vibrations and the sides of the material, whether it be just a side with gas on the other side or an interface with another material, depends on the size of the structure. Another example of a classical size effect, but one that becomes important at the nanoscale, is, for example, a measurement of the electroconductivity of a carbon nanotube versus its length. So we'll see this picture again next time, and we'll define the idea of a ballistic transport. And the idea and the definition of ballistic transport is, for example, the length over which or a transport where a carrier can go entirely through a material and not experience any scattering events. Or basically, the electron can go from one end to the other without hitting another electron or hitting the wall of the material. And this means that if you're in the ballistic regime for something such as a carbon nanotube, the resistance of the nanotube will not depend on the length. There are some quantum resistances that we'll learn about that relate to getting the electron into the tube and out of the tube, but there is no length dependence. And if you look way down at the bottom left of this plot here, you see that for very, very short nanotubes, you see a different relationship between the resistance and the length. And we'll expand upon this later. But then as the length gets longer, you have more opportunity for the electrons to scatter because their mean free path is now smaller than the length of the tube. And then you end up at the larger scale with the classical linear relationship between the resistance and the length, which is what you'd expect. If you take a piece of copper wire and you cut it to 1 meter long, it's half the resistance as if you cut it to 2 meters long. But if you were down to, say, 10 nanometers and 20 nanometers, and you also had a small diameter, then you may measure that the resistance of the tubes is the same thing. And we'll also learn how the temperature has an effect. For example, you have more scattering at higher temperatures because of the effects of thermal energy on scattering the carriers. And that means that that also affects the resistance. So the length over which you'd see this resistance-independent transport or this classical size effect would change depending on the temperature of the system as well. So if we look now for a minute at what's called the wave picture, we can consider that everything can be, every object, every particle can also be considered to have a wavelength. And the important length scale in this case is the wavelength of the particle, and the wavelength of anything is going to depend on its momentum and a constant h, Planck's constant, by this relation like so. And this is what's also referred to as the de Broglie wavelength. And by quantum mechanics, we can relate the energy and the momentum of waves by this relation here, where we say that the energy of the wave is equal to Planck's constant times the frequency of the wave, and we can relate the momentum to Planck's constant and the wavelength just by inverting this equation above. And we can define a variable k, which we will call the wave vector, and we'll use this in what we have in just a second. And the basic idea is that when the wavelength of our energy carrier is comparable to the size of the system, the waves are going to interfere in a coherent way. And this leads to effects of this wave interference and leads to the material having discrete energy levels. And this is what I'm going to call quantum size effects. So now, before we said classical size effects happen as we take the size of the system and we cut it down so the carriers are interfering with the geometry, but we haven't said anything specific about how the geometry is affecting the energy distribution of the carriers themselves. Now, in the case of quantum size effects, we can say we generally have smaller systems where the actual size governs the energy distribution and the allowable energies of the carriers. And that might seem a bit vague, but for example, we'll see in the case of a quantum dot, if you have a certain size, you're basically restricting the allowable energy levels of the electrons, and we can think of the excitation and emission of light from the particle as a transition from an excited state, a particular discrete energy level, to a ground state. And because you're changing the position of those different states as you change the size, because you're changing how the size affects the allowable levels, that results in a change of the color, or a change of that emitted photon energy as the drop happens. Whereas if you have something that's yay big and you change its size, you don't see any change in the color because all those properties are invariant when you're making much larger size changes. And if we look at the overall electromagnetic spectrum, you can see that we can have a broad frequency of waves and frequencies and wavelengths. And if we look at, for example, visible light, like the waves that are emitted by things that we can see, we see that the frequency is quite fast, is about, I guess this is 1 10 to the 15th or 1 terahertz. And the wavelength of light, as we've seen before in terms of length scales, is about a few hundred nanometers. And X-rays have higher frequencies and smaller wavelengths. That's also, because the wavelengths are so small and the energies are higher, that's why they can damage tissue. And things like microwaves and radio waves have longer wavelengths. So X-rays, because their wavelength is small, they can characterize and get quantitative information about materials, and they can penetrate things. And because microwaves and radio waves have bigger wavelengths, we can more easily block them with materials or shield them, for example, build things like Faraday cages as well. But we can consider this sort of wave spectrum in that all matter has wave properties as having a continuous possibility of different wavelengths and different frequencies. And then, of course, also different energies. And this chart is a summary of the transport regimes for different energy carriers that we've talked about. So now, if we have this picture of classical size effects and quantum size effects, or you could say a regime where carriers behave like waves, or we can consider their behavior as being dominant by wave behavior, or their behavior being dominant by particle behavior, we can see that if we have basically really, really small structures, we can adopt this wave picture, and if we have much bigger structures, we can adopt the particle picture. And all the details here aren't important for us, but I think this is a nice summary. For example, going up from the small length scale here up to a larger length scale. So going from the coherence length, or the length scale at which the waves that represent the energy carriers interfere coherently, and this being in the wave regime, up into a regime where the interference between the carriers is on the scale of the mean free path, and therefore where we can consider their interactions being more like those of particles, and talking about what we'll refer to as ballistic and diffusive transport. And here you can see that we go from, for the different energy carriers, describing the properties of materials or the transport, electron transport, heat transport, using theories of quantum mechanics, to using, for example, theories of ballistic transport, and for light, for example, ray tracing following the path of individual photons, to in the diffusive transport regime, where the collisions between the carriers, between the particles in our box or between the molecules are dominant, to describing the property of materials using the continuum and conventional laws that you've seen in other classes. So for example, in the case of things beyond the nanoscale, we talk about diffusive transport, and that's where Ohm's law may apply, or Fourier's law may apply, or Newton's shear stress laws may apply. But when we go down in length scale to the mean free path, and we go down beneath the mean free path, we need to start to have different ways of describing and understanding how the transport scales and how the properties of the materials change as the length scale varies. And both of those things can result in, for example, a difference in the definition and the result for, say, a thermal conductivity of material, or the electrical conductivity of material, or a practical thing such as color, as we'll see in a few moments. So I want to go through a little exercise that lets us present what really is the simplest example of how, in this regime of quantum confinement, we can start to think about the wave characteristics of energy carriers resulting in a change in the properties of a material. And the way we can start about thinking about this is think about two types of waves, which you might have seen previously or in math as well. And I want to define what are called traveling waves and standing waves. So a traveling wave is a wave whose intensity varies both in space and time. And you could think of looking at a traveling wave as standing fixed in space and looking at how the wave is varying in time, or standing at a particular instant in time and seeing that the wave is varying in a spatial fashion. And the difference, these pictures look identical, except the difference here is now if you're standing fixed in space, you're looking at how the intensity is varying in time as relates to the temporal frequency of the wave. And if you're standing fixed in time, you're looking at how the intensity is varying spatially, and that will relate to the spatial wavelength, what is being called lambda x here. And let's introduce another type or another way of looking at a wave, and this is a special case of a wave called a standing wave. And I like to think of a standing wave as like two people playing jump rope, where their hands are fixed and they're in synchrony moving the jump rope up and down like so. And in this case, we assume that we have the wave pinned at two extents. And these extents, like the distance between the people here, is a distance d. And in essence, what's happening here is mathematically the wave is constrained to have an integer number of wavelengths across this distance. So if you have one wavelength, n equals 1. If you have two, n equals 2. And if you have three, n equals 3. So if we look at this mathematically for a second, sorry, I need to insert a new slide, but it isn't letting me do it. So we can say that our wave phi, which we can sketch over here, where this is intensity and this is time, is equal to a constant A times the sine of 2 pi nu, the temporal frequency, multiplied by time, minus 2 pi times a unit vector in x, divided by the spatial frequency lambda x, times a unit vector in the y direction. And we can see that this has a time-dependent component and a spatial component. And this is what we defined as a traveling wave. So this wave is moving to the side as time goes past. And we can define omega as 2 pi times nu, where this is just our definition of the angular frequency. And we can define a wave vector, which we're going to call k, as k being equal to 2 pi divided by our spatial wavelength lambda x multiplied by the x vector, or just k x times x hat. So the reason I'm showing you this is because we can consider our standing wave, our standing jump rope wave, as the superposition of two traveling waves, one moving from one side and one moving from the other side. So if we take the sum of two of these traveling waves, one going one way in space and the other one going the other way in space, we can say that our phi of a standing wave is equal to our constant A times the sine of omega t minus k x, where now we've substituted omega as defined up here, and we've substituted k as defined up here, and added with a wave moving spatially in the opposite direction, or just omega t plus kx. And by sine and cosine relations, we can say this is equal to minus 2a times the cosine of omega t times the sine of kx. And so by our definition of the standing wave, where it's pinned at its boundaries, like so, and this distance is d, we know that at the boundaries here, we need the intensity to be equal to 0, or the wave is going to essentially have to vanish at the boundaries. So we can apply the boundary conditions that the intensity at 0 is equal to the intensity at d is equal to 0. And in the equation we had at the bottom of the last slide, we know that unless we have a specific constraint on the time that makes the cosine vanish, then in order to make this 0 at these particular distances, then we need the sine of kx to be equal to 0. So we need the sine of k times 0 to be equal to the sine of k times d to be equal to 0, which basically tells us that we have a constraint that d times 2 pi divided by lambda has to be equal to n times pi, based on the periodicity of the sine function, which tells us that the distance between these 2 points has to be equal to an integral of the wavelengths divided by 2. So maybe here it's just telling us mathematically which we would be able to we would have been able to guess by seeing this picture. But in the case of the quantitative constraint on the wave, in order to have the wave be standing, the wave has to be pinned at its ends by an integral number of wavelengths, or formally a half integral number of wavelengths. This is a half a wave, and that's a full wave, and that's 3/2 of a wave when a wave is one complete period of the fluctuation. So this is what we'll call sort of the one-dimensional constraint for a standing wave. And I'm doing this because we can arrive at a similar kind of picture by now taking an approach of quantum mechanics, or solving what's called Schrodinger's equation for the wave function, or the probability that that a particular piece of matter is at a certain position at a certain time within this idealized potential well. So now I'm going from this idea of having a wave constrained at 2 points, someone playing jump rope, to now thinking we have a particle stuck inside a box or a well here, and we want to understand how its allowable energy levels depend on the size of this box, or the width of this well. And it's kind of a very idealized picture, but basically what we're saying is that inside this well we have a potential that's forced to be 0, and at the extents of this well at position 0 and position D, you jump from having a constraint of infinite potential. So the particle can move around inside this space, but it can't get out because we have a constraint here of infinite potential. And this is what people call a one-dimensional potential well, or a particle inside a box. And this is the same thing we're going to think of as a quantum dot being, where the energy levels of the electrons inside this box are restricted because the size of the box is constraining the allowable waves for the energy of the electrons in it. And we're going to see that there are discrete levels that develop, and how that just qualitatively for us relates to the development of different energy bands. So if you've taken quantum mechanics, so you probably remember from physics, we can formalize this idea of treating matter as having waves by the case of a wave function, which we'll call psi, and the formal case of Schrodinger's equation, lets us relate the wave function and solve it to determine the energy distribution in time and space of, in principle, any matter, although it can't be solved except for very simple cases. So I'm just going to write out the full formal definition of Schrodinger's equation, and then we will take a simplified case. So the formal full Schrodinger's equation looks like so, where U is the potential energy, psi is the wave function, and H is Planck's constant. And you typically see H with a little bar on the top, which is just H divided by 2 pi, and M is the mass. And in a full definition, the wave function is the probability that the matter that it represents is at a certain position. Yes?
Probability amplitude.
Yeah, so it's a probability I guess you'd call it a probability density function.
Because psi star psi is the probability.
Okay.
It's a complex thing, so you gotta square it to get the probability. That's why they call it probability amplitude.
Okay. Okay. So I'll clarify this definition at the beginning of the next lecture. So in the case of, if we assume that we're dealing with a time invariant case where we eliminate time from the equation, we get what's called the steady state Schrodinger equation, which says like so. And this is the potential energy, and these values E are what we'll refer to as the allowed energy states or the eigenvalues. And we can apply this time independent equation to the simple case that we had a moment ago of the particle inside an infinite potential well with width d. And so if we solve this equation for this case, we would end up with a general solution of this wave function that we have the superposition of two exponentials, which the first one is like so, and the second one has a second constant b. Like so. And this applies on the case of x is from 0 to d. And now what we're interested in is what the values of E are that are allowed, or what the allowed eigenvalues are in this case. So you'll see in the notes that I'll post after lecture today that we can solve this just by applying boundary conditions to these exponentials, and we can convert the exponentials to sines and cosines, and we get a simple constraint that the size of the well is constrained by an integer number of pi. And this lets us rearrange this expression such that the allowable energies, or the eigenvalues, are related to or this should be regular h because of the pi. Are related to the width d of the well, and also are quantified by an integer n. So we can call this integer roughly a quantum number, and this says, in other words, that the spacing between consecutive energy levels gets smaller as the size of our box gets bigger. And so if we took, for example, the difference between two consecutive energy levels, we could define loosely a gap between one level and the next one. So the gap would be, for example, energy of a certain n plus 1 minus energy of the nth level. So we can have, as our n increases, we have different discrete levels, and the spacing between them decreases. And so as n increases, then the energy increases. but the difference between the consecutive levels decreases. And we've done this in this case for a one-dimensional case, but if, for example, we solved this problem for a simple two-dimensional case, then we could get another relationship that just told us that we would have two quantum numbers, two integers, L and N, and instead of an n squared, we had L squared plus n squared, and the final answer would look like this. But the idea here is not to get all of where this comes from, but get a picture that in a small state of the system, there are this idea of having these discretized or allowable energy levels. And in this simplest model, we can relate the allowable levels to the dimensionality of the system. So in the case of this simple potential well, that's like a zero-dimensional system, a nanoparticle. And in this kind of two-dimensional well, that's a more complex geometry, for example, having the restriction of the levels on a plane. And in a case that's, in a sense, what is happening at a high level in the picture that we saw before, where we're using a microscope to measure the electron density in this ring of atoms, which is placed on a substrate. And because of the energy distribution, the electron wave behavior of the electrons from one atom to another position, and because of the fact that they essentially interact with and reflect off this ring, we get an image of an atom here at the opposite position. So you have a ring of atoms here, and you have one atom here, and you get an appearance because of the interference of the waves that there is an atom appearing at the other spot. And remember, this was done by imaging locally using a tip and drawing out this picture like so, and by placing a ring of individual atoms around the surface like that. So now let me make another definition. We can see that now as we increase the size of material, we may be changing the number and the energies of the allowed states, or the allowed energies or modes, depending on what term you use to refer to it, depending on the types of carriers we're talking about. And so a general definition of what's called the density of states is like so, and the density of states is the number of allowable states for between a certain energy and a certain higher energy, E plus dE, per unit volume and per unit interval. And I want this definition to let us just think qualitatively that when we get down to this scale of quantum confinement, we're restricting the density of states, or the distribution of this density of states, as a function of energy. And in the case of a zero-dimensional material or a small box, we can derive that we have specific discrete allowable energy levels, and the reasons governing the shapes of these curves are not important to us, but rather the fact that we change the shape and go from a discrete distribution to a continuous distribution is what's important. And it's the interaction, basically the evolution of this density of states and the allowable energy levels in a material that determines the properties of matter and makes, for example, one crystal different than another, or makes the properties of the same material depend on their size. And as your material gets bigger, then you have a greater D, if you will, and you have more modes allowed, and things get blurred together. And then when you're changing the size at a large scale, there's not an important effect. But if we're in that D regime where we can consider the transport to be sort of like this one confined wave, then changing D will change our constraint on the wave character, and therefore change the allowable levels that we can consider. And I skipped over the past two slides because I want to get to the idea of a band gap. So as we go from this idea of the electron the allowable energies to how this lets us develop the allowable states of energy in a material, we would see that in general there are certain energies that can't be reached. For example, in a general space, we would have a relationship between the allowable energies and the wave vector, and you would consider that you have what's called a conduction band and a valence band. And basically, electrons or carriers can be excited from the conduction band to a valence band, and these unallowed energies define what are called band gaps, and this can be directly related, for example, to how materials respond to light. So if you have an electron in this conduction band and you hit the material with light such that the electron is excited into the valence band, you need to supply a certain energy in order to excite that electron from the conduction band to the valence band. And we can relate that sort of idea of a gap, or the difference between the allowable energy levels, directly to the simple picture we depicted for a small box, where a difference between two levels could represent in some ways this particular gap. And then when your electron is excited and decays back into the ground state, then it's going to release energy that was absorbed when it was excited, and it could release a photon of light. And it's the value of this energy gap that determines the energy of the photon that's released and determines the color of light that we see. And so combining this general picture where, in a multidimensional space of a real material, the shapes of these bands don't really matter to us, but saying that, for example, changing the size of our box changes this band gap, can therefore then change the wavelength or the energy of light that is emitted, can lead us to this general picture of how, for example, changing the size of material can change its color. And a lot of bulk materials have band gaps, basically because metals have a lot of free conduction electrons. They have zero band gap in their conductors, but semiconductors, because of the way their electronic structure develops, have finite band gap energies. And when we take the case of a semiconducting nanoparticle, what's happening is basically because of the effect of the size on the band structure, on that gap, the band gap of the material effectively depends on the size. And we can now relate this size-dependent band gap to the simple model of a one-dimensional well, and now see how the effective band gap of a small semiconductor crystal is essentially, in our case, that model that we had for the allowable energy levels in our one-dimensional well. And typically a band gap energy is quoted in electron volts, and for example for silicon it's 1.17 electron volts, and the other parameters in the table here are things we'll see in a minute, and this is a table that'll be useful for the problem on the problem set. So now we see our previous picture again, where we have different colors of quantum dots and that are now in a size range that we can imagine them in this small potential well, where now changing the size is changing the effective constraint on the electron wave function that determines the allowable energy levels in the material. And we have these two bands. We have the lower band, which we're calling the valence band, and the upper band that we're calling the conduction band. And basically what we've said is that electrons, because of the native characteristics of this material, cannot exist in this space. So if you hit the material with light with enough energy to excite an electron to this upper energy state, you can't end up in here, then you are going to create an excited state. And then when the electron decays back down to the ground state, light is going to be emitted. And a couple things are important here. One is that you will only get light emitted across the basic band gap of the material, not from a higher state to the ground state. So if you if you excite the electron to somewhere up here, for example, it most likely will decay what's called non-radiatively, will release heat or scatter in other ways until it reaches the lower tip of this band, and then it will cross the band, and then it will emit a photon with energy like so. And this can be also related to the same idea as the photoelectric effect, where we needed a minimum energy to excite that electron across essentially the energy gap of that system. And formally, when we hit this particle with light, we are generating an exciton because we're ejecting an electron to a higher state, and we're leaving the opposite, the hole, behind. And so when you hear about excitation in semiconductors or in quantum dots, you'll often hear about exciton generation and the idea of ejecting an electron to an upper state and leaving the hole behind. And so in terms of another picture, what's happening here is that when we hit the material with light, we're ejecting an electron from the conduction band where the electrons normally live up to this higher energy band that's allowed, and we leave a hole behind. And then when the electron decays, it's going to emit a photon with energy that is equal to the band gap of the material, and then you're going to revert back to the original state we had at the start. And what I want to say here is that because the allowable energy levels depend on the size of the quantum dot, the size of this gap depends on the size itself. And we can consider the transitions as being between energy levels that are defined for the electrons and for in the ground state and the excited state as a function of the size of this box. So if we were to take this system and solve the same Schrodinger's equation for a spherical potential well, considering the case of our ideal quantum dot, we can imagine that we have, instead of having a one-dimensional well like so, we have a spherically symmetric well with radius r or diameter d. And we would have a constraint that the potential energy at the outer surface is equal to the same infinite potential constraint we had in the case of the box. And so we could likewise write this steady state Schrodinger equation like so, where before I just had the u and the e collected on one side. And if we solve this, the details of the solution aren't important, but they're talked more about in Gapanenko, we would have that the allowable energy levels are in a similar formulation related to the diameter of the well and the zeros of the nth order spherical Bessel function which looks generally like this, and the zeros are the crossing points, and that's something we can look up. And where the mass here is an effective mass for the electron in the hole. And we can say that the effective mass here we'll also call mu, and mu to the minus 1 is equal to the mass of the electron plus the mass of the hole inverse. So this tells us the restricted energy levels in this small space. And therefore, if we want to build this picture of exciting from the ground state to the excited state, we need to now take this picture and build a diagram of the effective band structure of the material. So now, instead of having the parabolic bands, I'm just going to assume that we have flat bands, or we have these points like so, and we have a gap which is the bulk band gap, and then we have changes in energy that exist between the allowable levels for electrons in the excited state and holes in the ground state. And therefore, to quantify the allowable energy differences in this nanoparticle, we can say that this delta E for the nanoparticle is equal to the bulk band gap plus a change in energy on either side for the relative position of the electron and the relative position of the hole. And we're going to say these are equal, that the band picture is symmetric from top to bottom, and therefore we can say that the energy transitions are equal to the bulk gap plus twice times the result from before based on the effective mass times chi and L squared. And so this, based on the simple one-dimensional potential model, tells us how the allowable energy transitions for this nanoparticle are related to the bulk band gap of material and the size and these constants. And so you can imagine as the material gets bigger, then this term becomes negligible with respect to the bulk band gap, and the effective band gap or the effective levels have very small separation relative to the bulk characteristic, and the behavior is essentially that of the bulk. But if you have D being small relative to these, which are constants for the material and constants of this function, then these differences become substantial, and this represents the energy that is emitted when you consider N and L to be the lowest possible values when your photon goes back from the lowest allowable excited state to the highest possible ground state. And that's where we'll end for today, and I'll pick up next time with a few closing slides on this example, and then we'll talk about how this relates to electrical properties.